Hey guys, I'm Mr. C. Welcome to our lesson on similar triangles, similarity, and scale factor. This is our second geometry lesson. And here's your daily warm-up, right? So, this was basically proportions, right? Whenever you're dealing with similar figures, similar triangles, proportions is very, very useful. And all you do, you guys cross multiply. So 2x equals 4 times 7, which is 28. You divide both sides by 2, right? And you guys got x equals 14, right? And if you ever need to check it, right? Are these fractions equal to each other? 4/14 is in fact equal to 2/7. Um, Most of you did not have trouble with that, but well, actually, I'll jump over to number 2 here before I jump to 3. Um, this one, they want the ratio, a simplified ratio. Now, flutes to clarinets. So flutes, we have 51 of those things. Clarinets, we have 39. So I guess you could say 51 to 39, right? Also could be represented as 51. You might see like a little colon 39, or you might just see it written out as 51 to 39. I think that's it. I think that's the three ways they tend to be represented. And what you can do is you could reduce this just as you would reduce any fraction. And I'm just saying, well, what are the both of these both these divisible by a number? I'm looking, and definitely not 2 because they're not even. 3, well, the digits add up to something could be divided by 3. But to be honest, I mean, this is the kind of thing that most of you probably would need your calculus. Some of you guys knew this. Some of you guys knew the mental math here. So if I divide both sides by 3, 17 over 13, and I believe that is as far as you can go. In fact, it is definitely. So anyway, not just writing the ratio, but then also simplifying the ratio. Right. And then here, number 3, cross multiplied. Many of you, although you didn't have trouble with number 1, many of you had trouble with number 3. So we got 19 times x minus 1 and 6 times 3, which is, let me just see, 6 times, not 3, but 13 is 78. Okay, so the reason you guys had trouble with that, first of all, setting it up. Most of you didn't have trouble, but distributing, many of you forgot to do that. So we got 19x minus 19 equals 78. Okay, I'm going to add 19 to both sides, right? And you guys are all good at solving these two-step equations. When I add that 19 to both sides, 19x becomes 97, right? And then finally dividing by 19. Okay, and I believe, check my math, you guys. When I divide both sides by 19, I believe you get 5.1. Of course, I'm rounding just to one decimal place. I guess if you want 2, it would be 5.11. But yeah, there we go, 5.1. Yeah, anyway, so yeah, check my math on that, you guys. But that is the strategy there. You cross multiply, but then you have to remember to distribute. And then after you do that, it just becomes a two-step equation, which you guys are very, very good at. You were taught very well by your Algebra 1 teachers. Okay, now those of you guys that took geometry, these notes should look very, very familiar. They are from your geometry class, right? What is a ratio? Well, it's the comparison of 2 or more quantities. The big take home here is, well, the way that could be written 3 ways, and that they can be simplified. But then the extended ratio, that you could actually have a ratio of more than 2 things. Like a recipe, if any of you guys have ever cooked anything, those of you in culinary, you cook at something, that's what it is. It's an extended ratio. Typically you have more than 2 ingredients, maybe you might have 5, 6, 7, 8, 9 ingredients, right? And if you say that, hey, this recipe is for 4 people, but you want to make it for 40 people, right? Everything, you're gonna multiply everything by 10. Of course, sometimes it's a little more complicated. If it's a recipe for 4, and you want to, what if I just want 6? What if I want enough for 6? Well, then, you have to multiply everything by 1.5, which sometimes get a little challenging. Hey, a little challenge, you guys. There is one mistake in these reduced ratios. You guys probably remember this one from the warm-up. So that is not the mistake. See if you can catch it. All right, in class, most of you did. Yes, it was this one here. This should actually be 85. Right? And just factor out a 2 in both of those cases. And yeah, basically reducing ratios, you are factoring, right? So although this is a geometry lesson, right, notice factoring. In fact, the greatest common factor, probably the most important thing from, I think, that was our second lesson. We were factoring quadratics, right? Always factor out the greatest common factor. That is true with algebra, right? And that is true in geometry. So anyway, greatest common factor, that is a math skill across all the probability and statistics. I mean, across all fields of math, factoring out the greatest common factor is going to come up huge if you do it all the time. So that's my advice to you. Okay, and then what is a proportion, right? You saw us solve a proportion basically by cross multiplying. Number 11 should look very familiar. That was one of your warm-ups. But anyway, that's how you guys cross multiply. From what your Algebra 1 teachers tell me, you guys are incredibly good at cross multiplying. And solving proportions, again, is something that will come up time and time again, not just solving geometry problems, but for all sorts of things, especially that you guys that have ambitions of taking someday maybe Mr. Dunphy's AP statistics class. Proportions are absolutely everywhere, from basic math to the highest level of math. I mean, Mr. Dunphy's AP stats class is an example of that. Okay, now problems where you may use a ratio, right? Now these, again, may look very, very familiar. I took them straight out of our geometry course, so those of you guys have taken geometry. And basically, taking a word problem, this is a skill, a general skill, taking a word problem and making it into a math problem, right? That may be the single most important skill of all of these standardized tests, whether you're talking the MCAS, the SATs, advanced tests beyond that. This ability to translate a word problem into a math problem, probably the single biggest skill for your success, and something that isn't always focused on in math classes. I know in Algebra 1, your teachers did focus on it. They do an extraordinary job, but typical math classes do not focus on this stuff. So anyway, ratio of two complementary angles is 3 to 7, right? So we know complementary means they got to add up to 90, right? So if you say 3x plus 7x, that's how you would set that up, right? And here, supplementary angles, the ratio of those two angles are 4 to 1. Same thing, except they're adding up to 180, right? Geometry class, if this is bringing you flashbacks from what I remember from our class last year, students are very good at solving equations once they get to the equation, but that is the challenge, getting to the equation in the first part. So if you guys want a little visual here, imagine a 90-degree angle, right? You've got one, actually, that may not be drawn to scale. Let me try to draw it a little more to scale over here, right? So you've got your 90-degree angle, right? And then a ratio of 3 to 7. So if this was 3x, this is 7x, right? And you just solve for x. And ultimately, yeah, this would be 63. Once you get x equal 9, this would be 27, right? If you want a visual over here, right? Okay, so they add to be a straight angle. Maybe we call this x. Maybe we call this 4x. Right, if you want to, so this angle significantly bigger than that one. Anyway, that's some of you students really like visuals. I do, and some of you guys just like to crunch the algebra. I feel like doing it both ways is important, because remember, with this MCAS, remember you guys, this is just as much a getting good at MCAS questions class as it is a math review and reinforcement class. And that strategy of, does my answer make sense, right, is something that you need to be thinking about for every question that you answer. Does this answer make sense, right? So a lot of times these geometry problems, I know this is just our second geometry class, but by drawing the picture, right, you're much better able to answer that question, does it make sense? So anyway. Okay, scale factor. What the heck is scale factor? All right, so scale factor is, I mean, imagine you're blowing something up or shrinking something. So you're like a copy machine. You want something like twice the size or half the size or 3 times the size. That's what we're talking about, scale factor. you know, an example of scale factor might be of the blueprint for a house, right? Obviously isn't the same size as the house, right? That you need a scale to translate the blueprint or the drawing of what the house should look like, the floor plan, to the actual house that you are going to build. If you built a house the size of your blueprint, people would not be happy with the house. Except for little kids, they're looking for a dollhouse, right? Then they would be happy. But most people who are looking to live in that house would not be happy, right? So scale factor is very important here. So what is the scale factor of ABC to DEF? All right, so the next question, what is the scale factor of DEF to ABC, right? Okay, so I think what we're talking about here, right? So just to be clear, right, we're gonna look for matching sides. This is kind of a key to me, right? So AB, right, in order of everything matters here. The order of the letters matter. AB has to match up with DE. So we've got AB, which is 8. We got DE, which is 12, right? Okay, so so it looks like 8 to 12 can be reduced to 2 to 3. All right, so and notice the ratio, right? The first thing to the second thing, right? The first thing goes on top, and I'll just write that down. This is the first, and this is the second listed thing, right? And then what is the scale factor of DEF to ABC? Okay, so DEF. Okay, so I guess what we could do is we could take any two sides, right? So why not just take the same ones that we just had? 12 to 8, 12 to 8, right? Again, the first thing, right? This is just how they're listed here, to the second thing, right? And of course, that could be reduced to 3 to 2, right? And then what is the ratio of the perimeter? And yes, it will be the same, the ratio of the perimeter. Now, if you guys want to see this in action, how do I know? All right, so DEF, let's see, we got 12 plus 15 plus 27. I got my calculator here, 12 plus 15 plus 27. All right. And also, for you high-level math students, there is a mistake here that only the most insightful students will pick up. I want you guys to see if you can figure out what that is. All right, so those of you guys that are bored, like, yeah, Cotter, we know a scale factor, right? All right, you're that smart. What's the mistake? See if you guys can find it. All right, so then we got 8 plus 10 plus 18. All those add up to 36, right? That would be reduced there, right? So if you divide both the top and the bottom by 18, right? And so it's no surprise it would be the same thing. Did you get the mistake? All right, high level stuff here, you guys. The truth is, right, either one of these triangles would not be a triangle. Think about it. You've got one side that's 18, right? You've got this side that is 8. You've got this side that is 10. What are they going to be, right? Right? They would just kind of, these doors would just collapse on top of each other. They'd meet in the middle, right? So this would not actually be a triangle. Okay, so anyway, that's some higher level stuff. If you got it, great. If not, don't sweat it. That was just, yeah, both of these would not be real triangles in the real world. So just wanted to make you aware of that. All right, a real MCAS question. You guys have been saying, when are we going to get to the real MCAS questions, Mr. C? Well, here we are. Okay, a student plotted EF on a coordinate plane. The coordinates endpoints are, as they say, right, the students will dilate. What the heck does dilate mean? All right, well, dilate, and I know we're going to get deeper into transformations next lesson, but dilate basically means just blow it up, scale factor, or shrink it. Basically, use your scale factor to blow it up or shrink it. So we're going to dilate, right? So here we go. So I will first draw it, and then I'll show you what the heck we're talking about. So, so we will dilate EF. Okay, sorry if my thing isn't completely nice and neat here. So -2, 1. So to be clear, this is E, and then F is 1, -2. Okay. All right. So we will dilate EF, okay, by a scale factor of 2 with respect to point F. And again, so much of this geometry is overlapping, right? Transformations is something that we're really going to focus on next class, but this is kind of a sneak peek of that. But if we are dilating with respect to point F, right? If you're expanding something, blowing it up, what is the center, the point that is starting from, right? So what that means, right? If we're going to stretch this thing out, we stretch it out starting at F, right? So one way to do this, right? And I guess what I'll do is I'll say to create KL, right? So we are dilating EF by a scale factor. Okay, so it's going to end up being, truth be told, F is going to be the same as K, or one of them, right? And it's going to be twice as long. L is going to be like over here somewhere. Okay, so which graph correctly shows KL? Okay, so I guess what we're going to do is we're going to figure out what the length of this is, right, and double it, right, because our scale factor is 2. So what I might do, right, just to kind of make it easier on myself, I'm just going to say, well, hey, it looks like we're going up 4, right, and it looks like we're going over, wait a second, is that 4? No, it's up 3, right, because we're just to be clear what we're doing here, we got 1, -2, right, and over here, we've got -2, 1. So where am I getting this number from? 3, and I'll scribble that out, write it nicer. Right, we're going from -2 to +1. And here, we're actually doing the same thing, going from 1 to +2, so we're going over 3, right? So if I want to double this thing up, I'm going to do the same thing again. I'm going to go up 3. I'm going to go over 3, right? Now, you could use the Pythagorean theorem or the distance formula if you really wanted to get, I don't know. I don't know what the word. It's not crazy. It's not necessarily more precise because both strategies are equally good, but the logic of why this strategy works, it basically is the Pythagorean theorem. Going up 3 over 3, you're going to go up 3 over 3 again to double that, right? And so what's that mean? So if I go up 3 from 1, I've got 4, right? If I go over 3 from -2, I've got -5, right? And so that big segment that I'm talking about, I know I'm a little sloppy here, but there it is. That's the segment that we're talking about. Okay, now let's just see if one of the graphs matches. Okay, so it looked like I wanted to end on -5, 4, right? Wow, all these are pretty close, huh? Okay, so D is the right answer, right? D is the right answer based on the math and what I just did, right? But I just want to show you, because so much of these MCAS questions and any of these standardized test questions are just as much about recognizing wrong answers many times as it is finding the right answer, right? So if it's being dilated from point F, right, it's being stretched from point F. Now remember, point F and L, I may have flip-flopped them, but it's the same thing. So this thing is being stretched, right? The original segment, just to be clear, right, the original segment was from here to here. Right? That was the original segment, right? So it's being stretched from the original point F. Okay, so this one is kind of maybe stretched it kind of both ways. All of these are kind of stretched it both ways, except this one, which is kind of stretching it the opposite way, right? So anyway, that is the reason why D is the right answer. So all of these, I think all these segments might actually be, if you checked it out, the exact same length, right? And so they're just really testing here, are you dilating it from point F? Because anytime you stretch something, there's going to be a point that you're kind of stretching it from. And that's why D is the right answer. Okay, similar polygons. Okay, again, this is going to look very, very familiar because those of you guys that were in geometry class, which is the vast majority of you guys, actually, I shouldn't say that. Maybe it's about half of you guys. You've seen these notes already, and those of you that haven't, well, you're going to. So basically, similar polygons have the same shape, but different sizes, right? So if they were congruent, it's the same shape and size, but similar just means, you know, same exact shape, right? So basically all the angles will correspond or match up, and the sides will be proportional to each other. And just how does this all kind of tie together? The ratio of the corresponding sides is called the scale factor. And something from a couple slides ago you may remember is that if the sides are proportional, right, the perimeters will also be proportional. Okay, so let's just see some examples here, right? And basically the thing that just seems to come up on the geometry topic that comes up on all these standardized tests so often are similar triangles. And what is a similar triangle? Okay, basically what it means is that the angles, the corresponding angles are congruent and the sides are proportional, right? So so here like K, right, matches up with M, right? So they don't line them up side by side. They very rarely will. J matches up with P, right? And L matches up with N, right? Okay, that's kind of straightforward. Something that comes up very often are these overlapping triangles, right? Here, you know, Y is going to match up with obviously itself, right? And then R would match up with X, and Z would match up with S. Okay, and then the sides, you know, the corresponding sides would be proportional. Okay. The reason I think the similar triangle problems come up so often on standardized tests is because it makes you put together a bunch of mathematical concepts, right? First of all, you've got to recognize that you have similar triangles in the first place, right? And you have to match up the angles and sides, right? Because the order does matter for all of you that have taken geometry, right? So and those of you that haven't, basically what we're saying is A has to match up with D, right? B has to match up with E, and C has to match up with F, right? That's what we're saying, right? So first of all, you got to recognize you have similar triangles in the first place, right? You've got to match up the angles and sides in the appropriate way, right? You have to recognize that the sides, the corresponding sides, are going to be proportional, right? And then you have to use a proportion or your scale factor to solve for missing sides and things, right? So because you have to put together all of those mathematical skills and concepts, I think that's the reason why you will see these on so many of these standardized tests, specifically the MCAS. But hey, that's my idea. But hey, all you got to know is that they're going to come up. You are going to see similar triangles problems as long as you guys are taking standardized math tests. So here we have 18, right? We gave you some time to do this in class. I'm just going to kind of go through it because that's why you're watching this video. Right? You want to see me do it. So, all right, so we got similar triangles. Now, to be clear, right, the order matters a lot. So R matches up with U, right? S matches up with V. S matches up with V. And notice they're always going to twist these around on you. And T matches up with W. Okay. All right, so base of these dimensions of the diagram, what is the length in centimeters of VW? So they're trying to figure out this. So when you're solving a similar triangle problem for the missing side, this is what I do. I find two sides that match, right? Okay, so let's see. So UW is the one they're giving me here, right? UW is going to have to match, right? UW is going to have to match RT. You see what I'm doing there? It's the first and the last, right? So RT is going to be this, right? Always start with two sides that you know. And in order for this problem to be possible, they're always going to give you two sides that you know. So what I've got here is I'm going to say 6.5, right, is to 9.75, right? That is one of my proportions. And that is going to equal, now we're going to see what matches my mystery side that I'm trying to find. So VW has to match ST, right? So I got ST here, right? I got 5, and then I got VW, which is my mystery, right? And just to be clear, right, on this, in both cases, these are on top, right? On both cases, this is on, these sides are on the bottom, right? Just to be clear, right? Matching sides. Anyway, yeah, matching sides will correspond, right? So now, solving a portion, which you guys are very, very good at, I just cross multiply 6.5x equals 5 times 9.75. I am going to, should be close to 50. 9.75. Should be close to 50 because it's almost 5 times 10. 48.75. It is. Okay, now we got to just divide both sides by 6.5. X equals 7.5. And again, always, with any of these standardized test questions, I am always asking myself the question, does this make sense? Does my answer make sense? So first of all, it should be, since it's going to match up with the ST, right? It should be bigger than 5 because this triangle is bigger, right? It is, right? Now, sometimes because it sounds like common sense here, but if you flip-flop a fraction or something, right? You don't match things up the right way, you could very, very easily make a mistake. Um, so I just want you to always ask yourself that question: does my answer make sense? Okay, IXL preview. This is what you're going to see on your IXL. By the way, you guys have been killing it on the IXL. We're very, very proud of you. Anyway, I'm sure you're going to continue, right? What does it mean for shapes to be similar? Well, first of all, test number 1, the corresponding angles have to match up, right? So first of all, so angles, corresponding angles, congruent. Okay, these two match these two, those two match these two. So angles, boom, we got it. I'm going to check it off. The angles are corresponding angles are congruent. Now, are the sides proportional? Okay, that's my big question here. Okay, now first of all right, let's see. It looks like since this is looks to be an isosceles trapezoid, right? Because of that, I really only have to see are 3 sides proportional. Okay, so what I'll do, I've got the let's see, is this okay? So this matches up with this, right? So 19 to 23, right? Is that equal to, let's see, let's go 29 to 25. Okay. So now I don't have to do any math here, right? Now you could, sure. You guys could do a little math, find out that that's not true. But why is it obviously not true? Well, this is a fraction less than 1. This is a fraction greater than 1. So there's no way this is true. So right there, right, we've shown, right, 19, right, should match up with 23, and 29 should match up with 25. It doesn't. Okay, sorry, I don't know why that streaky thing went there. Hopefully that doesn't come up on the next slide. But right there, we know that this is not proportional. Uh-oh. Oh, okay. Okay, my tablet may be going a little haywire here, but that's all right. This is just the IXL preview. I'm going to talk you through it if I can't write you through it. Okay, so here we've got basically similar triangles. They want you to find J, right? And so first of all, what you guys got to recognize is what is congruent to what. So this these angles are congruent. C and E are congruent, right? C and E, right? And then D and F, right? So that will help you figure out what sides match up. Now you guys know how I do this all the time, right? DG, right, is going to match up with GF, right? So I set it up as 5 is to 10, right? And then here 4, okay, now 4 matches up with J, right? So 4 is to J. And just a little something that might help you check this, right? This in both cases is the top. This in both cases is the bottom. Okay, and I'm using the order of the letters to make sure that I'm matching the sides up appropriately, right? So you got DG, right? And you've got GF, right? You also have DC, right? And then the mystery side they're looking for, EF. So very important there, right? Now I do a little cross multiplication. What do we got? 5J is 40. You guys that have got it to this point, right? J divide both sides by 8, and there you have it, right? Those of you guys that wrote the proportion appropriately, right, would end up, with getting the right answer. Okay, so next, IXL preview. Which rule explains why these scalene triangles are similar? Now, I don't know if you're going to get an MCAS question that's asking you what rule makes them similar. You might. I know you get those kind of questions in geometry class, but you will definitely have to be able to identify similar triangles when it's not necessarily obvious that they are similar triangles. So you're going to have to basically pick these problems out of the, whatever, 40 questions you're getting on the MCAS, like, whoa, that's a similar triangle question, right? And use the properties of similar triangles to solve the problem. But which rule, let's just answer the question here, which rule explains why these are similar? Well, let's see here. I know that these two angles right, have to be congruent because they're vertical angles, right? That's why I know that, right? Okay. I also know that, well, if this is 36, this is 36, these are equal. Well, this has to be 50, right? Because there's only 180 degrees to go around. It has to add up to 180. So if you've shown that two angles are congruent, the third one has to be congruent. And that actually leads us to the reason, right? If two angles correspond or two angles match up, right? The third angle absolutely has to, and the reason is because triangles, the angles add up to 180, so it's kind of like a buy two, get one free, right? If you know you've got two congruent angles, you definitely have a third pair of congruent angles. Okay, this is the one that might be a little bit of a leap, especially because you guys, we haven't focused on transformations yet, right? So again, this is kind of a sneak preview. Some of you guys that are already former geometry students may not have so much trouble with this. Those of you that have not taken geometry may. But let me just talk you through it. So you could transform basically the yellow thing to the blue thing, right? Because yellow doesn't have little dashes, blue does, by translating it and then performing a dilation. Okay, find the translation rule and the scale factor. And again, a sneak preview of tomorrow. In fact, this is a very advanced sneak preview. But the first thing that you got to do, since a dilation is centered at the origin, so basically if you are blowing something up or expanding something, right, what is important is that it's from a particular point, right? So, oh, luckily one of these points is on the origin. So the first thing we want to do, right, is we want to move this thing down. It looks like we're going down 9, right? And then it looks like we're going over 3 to get E where we want it to be, right? So I guess what we would say is we're taking, so I guess we'd say the X is going, we're subtracting 3 because we're going from 3 to 0, and the E, the Y, I guess we're subtracting that. So that's what you would write. And by the way, if you haven't taken geometries, it's totally unfamiliar to you, that's totally cool, right? This is an advanced problem, right? And if you end up having to wait till tomorrow to be able to solve this, that's cool too, right? This is just something we're giving you advanced students who want and deserve to be challenged, right? So now what we've got here, since we're doing the same thing with every single point, right? We're going down 9, right? Here we go. Oh, and then we're going over 3, right? So this point, I guess 6, -9, right? And then over here, it looks like we're going same thing. Oh, I'm sorry, not -9, -6. Right here, same thing, we've got -6. I guess this is -6, -6, if I did that correctly. Okay, and so this new triangle, right, is after it has been translated. Oh, I'm sorry, it's not -6, it's -6, -9. Oh man, am I getting sloppy, you guys? I apologize. But anyway, now my red triangle, the red triangle to become a blue triangle. Okay, now, much like you saw when we did the dilation before, and again, if this is brand new for you, don't sweat it. This is, again, an advanced problem, right? 2 becomes 6, or 6 becomes 2, right? So what it is here is your scale factor is going to be 1/3. And really, you could just take 1 point as long as you translate appropriately, and you would be able to figure out the scale factor. Scale factor, by the way, how do you find the scale factor? Just a little something to figure out the scale factor if you were asked what the scale factor is, which you are in this problem. The way that you do it, it is the ratio of the, I believe it is the new to the old, right? So the new to the old, right? So why is it 1/3? Because the new thing is smaller. Okay, so anyway, that is with scale factor. It's the new thing over the old thing. Also, I mean, I guess you could also write it as the new, right, to the old, right? That would also be a ratio. But more often, it's written as this. Okay, anyway, we've covered a lot today. Anyway, I hope you guys enjoyed this video, and I look forward to seeing you guys in class. And as always, if you have any questions, feel free, shoot me an email. Stay late after class, right? Myself, Miss McNally, we are more than happy to help you with anything that you would like, even if you think it's something you should have already learned. Keep in mind, even if you have learned this, it's been a while, right? So there is no shame in having to do a little extra review. All right, you guys. I look forward to seeing you in our next class.